For those of you who are already here, if you want to scan the QR code in the middle of the screen or use the URL below that, you can find the today's materials in the folder that starts with today's date. We'll get started in just a couple minutes to give everyone a chance to join. All right, well, thank you everyone for joining today's GDS tutorial. My name is Julie Butler and I'm the secretary for GDS, and I'm happy to be here with Jane Kim, who will be giving today's tutorial. Before I turn it over to Jane, I have a few announcements. If you would like to provide any feedback to us on this tutorial series, please scan the QR code on the left side of the screen. That will take you to an anonymous Google form where you can give us anything you think we should continue to do or anything you think that we should change on how we do these tutorials. The middle QR code will bring you to the materials for today's session. This will take you to the GitHub page for all of the materials for the tutorial series. They're organized by date. So the materials for today are in the folder that starts with today's date, so 112125. If you're not already a member of GDS, but you find some benefit in attending these tutorials, I encourage you to join GDS using the QR code on the right side of the screen. It would only be a small fee in addition to your normal APS membership, and it does help us a lot to have more members in our unit. If you have topics you would like to see at future tutorials, or if you have speakers you think would give a good tutorial in the future, I encourage you to send me an email at this email address with either a topic or a speaker, and we encourage self-nominations if you would like to do one yourself. I would like to remind everyone that as an APS event, we are governed by their code of conduct, which means that we should all be respectful towards one another and all people. If you would like to read the APS code of conduct, please use this QR code here or use the URL below the QR code. If you would like to view the recordings for past tutorials, we have a playlist on the APS YouTube channel, which you can find here. Our next tutorial will be on December 5th, and I will be emailing you all details about that soon. And so with that, I will turn the floor over to Jane.
All right, thank you so much, Julie. I will share my screen. And okay, and everybody can see?
Looks good.
All right, perfect. Well, thank you so much for everybody joining in online. My name is Jane. I'm a postdoc at Argonne, and I work on these things called neural network quantum states. I'm really excited to tell you about them today. So in my opinion, neural quantum states is one of the most promising ways that we can reach larger and larger fermionic systems in a completely ab initio framework. Today, we won't get to the full many-body problem, but I want to give you a flavor of how these neural quantum state calculations go and kind of give you a sense of the fundamental building blocks so that you can work your way up into a many-body system. So let's start with a brief introduction. I really quickly, I see some things. Oh, sorry, Julie, that's you in the chat. Okay, so let's start with a brief review on some basic quantum mechanics. So say I'm trying to solve the non-relativistic Schrodinger equation in the time-independent Schrodinger equation. This is just a simple eigenvalue problem where you have your Hamiltonian acting on your wave function, where the Hamiltonian contains all of the kinetic and potential energy terms and governs the interactions between the particles in your system. Your wave function encodes all of the information about your system, and then you have the associated energy. And your goal in solving this Schrodinger equation is to find a pair, an eigenpair, your wave function and the associated energy. So instead of solving the problem, let's think about what it takes to just write down a single state. Say I have a very simple system of just a spin. This can be in a superposition of spin up and spin down. So I need two complex numbers to fully characterize the state. So if I wanted to store that in a computer, I need two complex numbers formed in a vector, and that can be an explicit form of my wave function. Let's add another particle into my system. Now, with two particles, I now have four complex numbers I need to store in a vector. If I have three particles, I need eight numbers. Four particles, I have 16 numbers. And in the general case, if I have n particles, I need 2 to the n different complex numbers to fully write down the state. So at this point, I'm not talking about manipulating the state or solving for it, dealing with the Hamiltonian at all. I just want to write down what a single state, what kind of memory resources we would require to write down a single state. You can see that it grows exponentially. And this is the crux of the many-body problem. By nature, quantum systems have this exponential scaling of Hilbert space. So in order to deal with the fact we have finite computational resources, we need to be more clever about how we solve the many-body Schrodinger equation. We need smarter approximations so that we can actually contain as much of the physics as possible without using all of the computational resources. And in the ideal case, we want a method that scales polynomially with the system size or, for example, the basis size. There are a lot of different many-body methods out there. So why should you even care about neural quantum states? You might have heard of Hartree-Fock, for example, or many-body perturbation theory, density functional theory, and these all have their pros and cons depending on the strength of your interaction or the type of system that you're working with. But quantum Monte Carlo, which is kind of the umbrella family of methods that neural quantum states falls under, is particularly adept at situations where you have very strong interactions or very subtle correlations that are difficult to capture with many-body perturbation theory, for example, or coupled cluster. So in this case, in quantum Monte Carlo, the problem is you typically have this fermionic sign problem when you're dealing with systems of fermions. So that's one. Another problem, though, is that you need to very carefully construct a good trial wave function in order to get your quantum Monte Carlo method to even work in the first place. So the point of using neural quantum states is to solve these two issues, how to deal with the sign problem and how to have a more general form of your variational wave function so that you're able to scale up and scale up your calculations to larger systems and also explore different Hamiltonians that you might be interested in. So instead of carefully constructing your wave function for every Hamiltonian you encounter, you instead have something more general that you can throw at the problem. Now, the specific kind of quantum Monte Carlo method I'll be talking about today is called variational Monte Carlo. For the most part, it's sign problem free. So I'll talk about this in a little bit more detail later. But the idea of variational Monte Carlo is very simple. You might have heard of the variational principle in your quantum classes. And the idea is that for any Hamiltonian and any choice of your wave function, if you take the expectation value of the energy, it's always going to be greater or equal to the true ground state energy of your system. So this gives us a way to, instead of like solving for all of the different states within your many-body system, you just target the ground state and you turn the eigenvalue problem into an optimization problem. So imagine then, instead of just having any wave function, I parameterize it in terms of some numbers, and I minimize the expectation value of the energy with respect to those numbers. So that's the basic idea of any variational method. But I was lying a little bit. You can't just use any choice of wave function. So imagine I have this Hamiltonian, and my wave function is symmetric with respect to particle exchange, but I'm trying to actually find a fermionic system, the ground state of a fermionic system. Then the energy that I will get with a symmetric wave function, it will always be lower than the true ground state energy of the fermionic one. So by restrictions apply, I mean that this wave function needs to have the right symmetries and the right boundary conditions in order to actually characterize the state that you're looking for. So these are some very important caveats in constructing this wave function and incredibly important when you're using something flexible like artificial neural networks to parameterize your wave function. Now, the second part of variational Monte Carlo is the Monte Carlo part. So where does this come in? So this expectation value is a very high dimensional integral. And this is especially so as you add more and more particles into your system. So a way that we can handle the dimensionality of this integral is using Monte Carlo integration. This is the most practical way to approximate a high dimensional integral. The idea is like this. So say I have some integral and it's defined by integrating over x over some normalized probability distribution that weights the values here of f of x. Then I could approximate this integral as a discrete sum over these function values evaluated at samples coming from your probability distribution here. So in order to sample from this probability distribution, there are a lot of different techniques you can use. The one that we'll be using for neural quantum states is something called Markov chain Monte Carlo, because the important thing is that our wave function is not necessarily normalized at this point. So to deal with the fact that our wave function is only known up to some scaling factor, we'll use Markov chain Monte Carlo because it's a special case where that normalization factor cancels out. And the idea is something like this. I start at some random place and I propose a move to some other place and I measure what probability that at the ratio of probabilities between my new position and my old position. And that's going to tell me whether or not I take this move. And I take that move stochastically. After I do these steps many, many times, I should converge to the underlying probability distribution without ever having to calculate an explicit normalization factor. So that's the basic idea here. So where does this come in? So let's turn a general expectation value of some operator O into a Monte Carlo integrated quantity. So if I write out these integrals, it looks something like this. Psi star evaluated at x, my operator applied onto my wave function here. I'm going to insert a 1 in between the operator and this wave function here on the left. And I end up with a quantity here that is exactly a normalized probability distribution, P of x. And the quantity on the right is what I was calling f of x before. So if I use the formula from the previous slide, then I can evaluate this integral as a discrete sum over what I'm going to call a local operator. So for the energy, this would be like the local energy. And these xi's are the positions that I sample from my wave function squared. So now, how do neural networks fit into this kind of construction? So I said I wanted to build a variational wave function in terms of artificial neural networks. The input to this entire method is some assumed Hamiltonian, and of course, the symmetries of the system that you're looking for. So the input to the network are they're going to be the many-body configurations. So all of the positions, and let's say I'm working with fermions, maybe I also have spins included in these configurations that I sampled discretely. But the output is going to be the amplitude. This is going to be the wave function value evaluated at this configuration. And the way that we train this neural network is by minimizing the energy through either gradient descent or something more sophisticated like stochastic reconfiguration. So these are just some small details. And the workflow is like this. I sample a bunch of configurations, a bunch of many-body configurations from the wave function squared. And I do this using this Markov chain Monte Carlo integration or the Markov chain Monte Carlo sampling. And then I use Monte Carlo integration to evaluate the average energy and also the gradient of the energy with respect to the parameters of your wave function. And then I use that gradient and gradient descent to update the parameters. And you continue doing this loop until you are satisfied with your convergence. Now, I think in some of the other tutorials, you might have already been exposed to feed-forward neural networks. And at this point, I don't want to go too much into the math, but I just want to give a high-level idea of what these feed-forward neural networks are. So when you work in continuous space like me, these feed-forward neural networks are usually the best choice to build your larger networks from. So these are the fundamental building blocks. These are inspired by the structure of the brain. And the nodes are organized into these layers that makes it efficient for computation. The connections are only in between neighboring layers, and information only flows in one direction. So this means that when I go backwards, I can just use the chain rule in order to differentiate my wave function or my neural network. Now, the components of a feed-forward neural network are very simple. It's just alternating compositions of two types of transformations, and a fine transformation that's very fast and trainable, and also a nonlinear activation function that's applied element-wise on all of the nodes. And these are very simple, fast, and they are not trainable. So this helps when you're, differentiating your wave function that all of this can be done very quickly. Now, feed-forward neural networks are special because they have an associated universal approximation theorem. This just says that if you have a feed-forward neural network with one hidden layer and enough hidden nodes, it's not guaranteed that the number of nodes doesn't grow exponentially, then it should be able to approximate any continuous function on a compact domain to any desired accuracy, as long as you just let that neural network grow. Okay, in practice, we don't actually just make our neural network wider and wider. We typically try to make it a little bit deeper and deeper, but then you also have the problem of your gradient then exploding or vanishing. So we have to be a little bit careful as our wave functions grow and grow, but nonetheless, these feed-forward neural networks are really important for building our more complicated neural networks. And I also mentioned this using the chain rule, that formally this is called backpropagation when it comes to feed-forward neural networks. Now, I've already talked about three of these building blocks that we typically use to build a many-body wave function. So linear transformations, translations, and also activation functions that add nonlinearity into our transformations. Two of the ones I won't be focusing on too much are pooling operations and concatenation operations. These are very useful when you're trying to build correlations into your wave function, or if you're trying to enforce certain symmetries. You'll see that the tutorial, the coding tutorial later on is a particularly simple case where we won't have to deal with these operations, but I wanted to mention them here because for the many-body system, we really use these pooling and concatenation operations very extensively. Also, keeping at this kind of high level, let's just imagine what happens to some domain as it passes through a feed-forward neural network. So let's say I start with this shape over here in R2, and I apply a linear transformation plus a shift. What that's going to do is allow for some kind of rotations in this plane and also some stretching and squeezing. And I can also shift. So after this, I can then apply a nonlinear transformation, and I end up with a shape that can be fundamentally different than the shape that I started with. And I can apply this over and over again. Now I took that last shape and I'm going to apply another linear transformation plus a shift. I can end up with something like this, for example, and I apply another nonlinear transformation and I end up with something even more different than what I started with. So this is just to schematically show that even though feed-forward neural networks are made up of very simple building blocks, when you apply these different layers over and over again, the transformations that you can describe are very different and they have a wide range. Um, Now, at least, okay, for many body systems, this is pretty important to know is that typically when we have a highly correlated system, it's often easier to temporarily move into a larger dimensional space in order to tease out those correlations before moving back into a scalar quantity like your wave function value. So this is just to schematically show, let's say I have a bunch of data points that are given to me in this one-dimensional form, but if I temporarily transform into a higher dimensional space, I'm able to separate these two different categories in a much easier way. That way I can then tease out the correlations and then I can move back into a lower dimensional space. So oftentimes with many body systems, we apply these higher dimensional embeddings in order to more easily find correlations between the particles in our system. And at this point, I just wanted to show you some of the progress that has been made over the last few years on continuous space systems in particular. So for example, with homogeneous electron gas, there's this interesting phenomena as you go to lower and lower densities, you find this formation of a Wigner crystal, this floating crystal. And in order to actually see this crystal arise, you need a way to capture very subtle correlations arising from the long-range Coulomb interaction. And you have to be able to simulate many particles to really see a signal of this crystallization. So the only way to really do this is to have a compact wave function. The way that we've done this in the past is using a message passing graph neural network, also with an attention mechanism. I won't go too much into the details, but the point is that we can have a much more compact representation of the wave function compared to other neural quantum states that have been applied to the same problem. And we can see the signatures of this Wigner crystallization at very, very low densities. Another challenging case is in ultra cold Fermi gases. So think of a superfluid, for example, where you have strong pairing correlations. And when this interaction is extremely strong, it can be very difficult to apply traditional many-body methods to a system like this. This is because the interaction range is very short, but the scattering length is very is basically infinite. So after a variational calculation, what you're ended up with is a wave function, and you can then extract all kinds of information from it. So this is just to show that for the unitary Fermi gas, we're able to handle these short range correlations. As you can see, as the effective range goes down, the peak of this distribution goes up. And notice that this is also on a log scale. So this is showing how flexible our wave functions really can be, as well as being able to characterize very different types of pairing correlations that are around this unitary limit, this particularly strong limit. We can also scale up these calculations even for a very challenging case like the unitary Fermi gas. We can scale it up to 66 particles, for example. And compared to diffusion Monte Carlo calculations, we do significantly better, but we still have some discrepancies between the auxiliary field quantum Monte Carlo calculations, which are sign problem free and are on a lattice. So it's slightly different since these methods, this variational Monte Carlo with BCS, DMC with BCS, and VMC with these neural quantum states, they're all continuous space models. I'll skip that one. And in nuclear physics, this is particularly exciting to deal with this scaling, right? Because in nuclear physics, variational methods can provide very high resolution calculations, but because of this exponential scaling of Hilbert space, it's been very difficult to move past about 12 nucleon calculations. But with neural quantum states, we have been already reaching to nickel 58. And we've also tried lots of different interactions to try and characterize, what makes matter bind together. And like I said before, we're ended up with some wave function. We can then calculate any observables from it, any information that we want to extract. So here are just the charge radii. And finally, we can apply the same neural network construction to nuclear matter. So here we have a bunch of nucleons in a periodic system of nucleons at a relatively high density. But as I lower and lower the density, the symmetric nuclear matter, you can see that these clusters start to appear. And this is not something that we have put into our calculations at all. The only thing that we're changing here is the size of the box because we're just modulating the density. This is coming directly from the interactions that we assume between the particles. So this is a really exciting way to show that this clusterization appears naturally from the interactions themselves. And finally, I've made a big deal about scaling. Scaling with this type of method is extremely promising as it gives us a way of tackling much larger systems. And I'll skip some of these. And so I hope I've convinced you that neural quantum states can give us a chance to reach very large, strongly correlated systems, larger than ever before. And it's an exciting time to be in this field since neural quantum states are still in their early days, but a lot has been done already. There's still significant room for improvement. And now let's transition into a coding tutorial where we aren't dealing with a many-body system. We're dealing with just one particle in one dimension. I want you to be able to see the neural networks learn yourself. Okay, so let's now transition to this notebook. You can find this notebook in this repo, Julie's repo, GDS virtual tutorials, and today's date and NQS. I have opened the completed version of the IPython notebook. Also note that there's this other Python file here, neural quantum state utils. So I'll describe a little bit about that after we kind of get situated. I'll give you a few minutes. So to run this notebook, you'll need some dependencies, which I have included in a cell. Hopefully it's all of them that you need. And while you're getting set up, I just wanted to mention this package called netcat. So if you want to go into more detail about using these neural quantum states, there already is a Python package that allows you to play with these, especially for spin systems at the moment. Today I'll be focusing more on continuous space systems because that's just the space in which I live. But if you want to play more, I highly recommend using netcat. For the most part, I try to make this notebook without much assumptions about your coding background, but I will be using a package called JAX. This just helps our code run faster. I'll describe in a little bit more detail later on. Okay. So we went over a lot of these details already, but let's emphasize a few of these. So recall that this, given some Hamiltonian and any wave function, the expectation value is greater than or equal to the true ground state energy of the system. This is the integral we're trying to evaluate. We use Monte Carlo techniques in order to evaluate this integral and its gradient. And one thing I didn't really mention much of is a gradient-based optimization, but this is very similar to what already exists in a lot of other machine learning fields. Within neural quantum states, there's a method called stochastic reconfiguration that's very similar to the natural gradient method. It's actually exactly the same as the natural gradient method. basically. And it's a second order method that's more often used. But for this very simple case, it's perfectly fine to just use a first order method like atom. One question that I get a lot is, what is the training data here? And I want you to remember as we're going through this notebook, the training data is something that you will be collecting yourself during each iteration of the training process. So there isn't some wave function that I've found through some other method. I'm handing it over to you and you're learning this wave function or you're fitting this wave function. The wave function you'll get at the end of this notebook emerges directly from the Hamiltonian that you assume. So there is no external data sets that we're using in order to learn this wave function. I said this before, but the general algorithm goes like this. I generate my training data, so I sample configurations using Markov chain Monte Carlo to sample from the probability distribution given by my wave function. I compute the cost, which is the energy of my system, and the gradient using the sampled configurations, and then I update the parameters using gradient descent. So I repeat this until it's converged. And neural quantum states are particularly useful for strongly correlated quantum systems, especially fermionic ones, when you increase the number of particles in your system. These neural quantum states typically scale polynomially, so maybe between n squared and n to the fourth is pretty typical for us. And in contrast to the factorial or exponential scaling seen in many of the other many-body methods. And after you design some trial wave function, you can often switch out your Hamiltonian relatively easily, within some restrictions, of course. As I've described, your wave function has to have certain properties depending on what type of system you're trying to characterize. And of course, the sign problem. The sign problem is something that comes up whenever you deal with fermions and with Monte Carlo in the same room. In this case, because we're only dealing with one particle, you won't have to worry about this, but it's something to keep in mind of if you try to extend this notebook for more than one particle and you're dealing with fermions. You have to deal with this anti-symmetry, and then you have to deal with the sign problem. But what's nice about variational Monte Carlo is that you're always sampling from the wave function squared. So there's no ambiguity on what the sign is. The wave function at any given point of the training process is always analytically known. And the sign is always known. So this notebook is very simple. We're not dealing with a many-body problem here. We just have a simple toy problem. And I would like for you to visualize the training. So you'll see that towards the end, you'll create some animations of your own. And when I talked about feed-forward neural networks before, it was purposely a little bit vague, but let's make it more concrete now. So the affine transformation, so the linear plus the shift, is characterized by a weight matrix W and a bias vector B. So I take in my input to this layer, apply my weight matrix, and I shift it by B, and then I get the output of this affine transformation. And then I apply a non-trainable, element-wise, nonlinear activation function. One thing to note, which is a little bit different than a lot of other machine learning problems, is that we have to be a little careful on what kind of activation functions we choose. For example, ReLU is something that's used a lot in different contexts in machine learning, but it's something that we typically, or we just never use in variational Monte Carlo, especially in continuous space. The reason is we want our eventual wave function to be twice differentiable because the kinetic energy term includes a Laplacian, right? So we want our kinetic energy to be continuous as well. So we only choose activation functions that are at least twice differentiable and continuous. Now, These are the two fundamental transformations. We apply them over and over again until we get our output. And in this case, we'll use a linear activation function for the final output layer, or which is the same as no activation function at all. This gives us an unbounded output. And I'll show you why we do this in a little bit. And then what I've been calling theta up until now, so the collection of all of the parameters in the network is just all of these different weight matrices and bias vectors for each of the layers. I think at this point we can just look a little bit about into this NQS utils.py file to see how we construct this neural quantum state and store these weight matrices and bias vectors. This is probably not the way that you would do this if you're trying to write a really nice code. Okay, but I'm trying to be as explicit as possible just for this tutorial. So here I want to build my wave function and I'm going to store my parameters in this big list. I loop over the layers and I just want to know what is the dimension of my input, what's the dimension of my output. I define some widths to sample my initial parameter values, and this is dependent on the dimensions. And then I just sample some random weight matrices and bias vectors, and I just store them. So it's the same kind of construction I've written here, where I just take all of these weight matrices and bias vectors and squish them all together. And what I'm left with is a big parameter vector. Notice that this is a list of tuples of arrays of different sizes. So we call this a pie tree, and they're very useful to know and to use. And JAX really allows you to use pie trees seamlessly. Now, moving on. I mentioned that our wave function has to have very specific properties to be even considered a wave function. So for this one-dimensional, one-particle case, let's think about what kind of properties our wave function needs to have. Of course, it needs to be continuous. It needs to have a continuous first derivative, also needs to have a continuous second derivative, as long as our potential is at least twice differentiable. We also want it to be positive definite. The ground state of a one particle system is always going to be positive definite. So we'll use this to remove contamination from any non-physical states, non-physical ground states. We also want this to be normalizable and bound, meaning that the tails of the wave function go to 0 when x becomes very, very large. So we'll do this in practice by imposing a big envelope that encourages the tails to go to 0. It's very difficult for the wave function to fight this, a neural network to fight this, so it typically doesn't. Now let's say that this big f of x is some unconstrained neural network. And by unconstrained, I mean that the output activation function is linear. So this output can take any value you want, both positive and negative. And then we also need to choose an activation function. We want to make sure that it's twice continuously differentiable. And because we want our eventual wave function to be positive definite, we're going to apply an exponential after we pass our information through our neural network. To encourage the tails of the wave function to go to 0, we're going to apply a Gaussian envelope. And so when you combine all of these different things together, what you end up with is a wave function that's exponential of the output f of x minus some parameter c, which is typically very small, like 0.01 or so, and x squared. Now, what you'll see oftentimes is because we need to calculate acceptance probabilities during the Monte Carlo walk, we have to divide probabilities together, and there's a little bit of a risk when your probability becomes very small. So what we work with instead is our wave functions in log space, and this allows us to take these ratios of probabilities in a slightly more numerically stable way. So we'll work with a log of the wave function throughout this notebook. Now, to sample, we, like I said before, with Markov chain Monte Carlo sampling, we don't have to worry about this normalization factor. And we can just work with the square of the wave function itself in order to eventually construct our chain and which represents the samples from our wave function. The idea is to just start at some random initial state, and then we generate a new candidate by perturbing it, usually symmetrically. And then we accept or reject this new move by computing this acceptance probability and throwing a random number between 0 and 1 and comparing it with this acceptance probability. If this random number that you've drawn is less than A, then you accept the move. Otherwise, you leave your state unchanged. And you repeat this over and over again until you've constructed your chain. But one thing to note is that if you randomly perturb your initial state by a very, very small amount, that means that even if you accept the move, your new position and your old position are very, very similar. They're highly correlated with one another. So in practice, what we need to do is throw away some intermediate steps so that we can get rid of this autocorrelation. Another thing is that depending on which initial values you choose, like let's say that we just sampled our positions from some Gaussian distribution, but it wasn't quite the right one, then it's going to take some time to equilibrate towards the true probabilities of distribution given by our wave function. So we also need to throw away some samples from the very beginning. So this is called a burn-in stage. We throw away a large chunk at the beginning, and then we throw away a bunch in between some of the effective samples that we actually use for our calculations. So before we move on, let's look at how the sampling will look. So here is the sampler class. I define the number of chains that I want to propagate and the number of samples per chain. NEQ represents the number of equilibration steps or the number of burn-in steps before collecting the samples. And I'm also going to skip some number of samples in between every single effective sample. Sigma step and sigma init are going to define the size of the step I'm taking during each proposal and the size of the Gaussian that I'm sampling from initially. And then, of course, this is the wave function that we pass later on. You'll see throughout this code that I use this JAX-JIT. All this means is it's just in time compiled. So anytime that I run my code and it encounters a JIT compiled function, it will process what's there and store it in memory, store it in cache, so that the next time it encounters this function, it's extremely fast to execute. So one thing about using JIT compilation is that the first time you run the function in question, it's going to be a little slow. That's okay because every call after that is extremely fast. So the details of this is not too important for us. All this is just proposing some random moves. I take my old position and I perturb it a little bit using some Gaussian kick. I compute the new value of the wave function at this new position, and I calculate the acceptance probability using the log of the wave function. I throw a random number to determine whether I accept or reject this new proposal, and then I return the new state. I run this exact loop over and over again. I'm just going to skip over all of the intermediate states so that I can reduce autocorrelation. And when I actually sample, I want to do this for many different chains at once. Here, I'm just skipping over the first NEQ samples to equilibrate all my chains. And then I store all of the history except for the skipped samples in between. And then the samples that I end up with for my wave function are just all of those individual samples that are all flattened into one vector. All right. By the way, if you have any questions, just let me know. You can chime in anytime. Okay, so I've mentioned using JAX. I showed you a little bit about what just-in-time compilation does, but I also use vectorized mapping and automatic differentiation. So let me show you where that comes up. First, I define what it means to apply my neural network. So this is that capital F of X that I was talking about before. And my wave function, or the log of my wave function, is defined by F minus C times X squared. Now, in order to evaluate the log of my wave function over many different positions, not just one, I can use jax.vmap in order to do this calculation in one big batch. So this is very convenient because we're dealing with many samples, and I want to be able to do the same kind of calculations over every sample. Now for the gradient, where that is useful is in the Hamiltonian. In the Hamiltonian, there's a second derivative that appears. And so I can use jax.grad to differentiate my wave function. So this is a very nice way. This is one of the most important reasons to use JAX in the first place. But there are a lot of other packages like PyTorch, for example, that does something very similar. Okay. I've talked about computing observables using Monte Carlo integration. If you want some more resources on using JAX, especially it's a little bit finicky when you're using random numbers. But once you're used to it, it's pretty intuitive. And there are some other resources here about working with PyTrees. Now let's actually start running this code. If you haven't already, you can run this cell to make sure you have all of the requirements needed for this notebook. I've already run this. Maybe I'll just do it just in case. Sorry for jumping around. I'm going to import JAX here, check what version I have. If you're opening this notebook using Google Colab, I would run this cell and make sure that you have this NQS utils.py visible to you. I'll skip this cell for me. And then let's import all of the classes defined inside of this file here. Now, neural quantum states, you've seen little bits and pieces of this class so far, but in order to construct my neural quantum state, I need to define the number of layers it has, the number of nodes in each layer, activation function, and this parameter C that defines how confined our wave function is. So a good number to use here is 0.01 or 0.04, for example. I've listed some of the nonlinear activation functions that I recommend. I typically use GLU. Next, to construct our sampler, we have to specify the number of chains, the number of samples per chain, the number of equilibration steps, the number of samples to skip in between each effective sample, the size of the Gaussian step in the proposal process, and also the size of the Gaussian that we're initially sampling from to start our chains. And then finally, the wave function that we just described. Now, the Hamiltonian can be anything that you want. In this particular case, we've defined the Hamiltonian for a one-particle system using potential as input. And this is because I'd like for you to be able to experiment with different potentials if you want to in a nice way without actually having to change the class itself. The important part of the Hamiltonian class is just the definition of the kinetic energy. Here I've assumed that h bar and m are both equal to 1. There are some other useful functions here, being able to calculate the mean and the error over your samples, taking gradients with respect to your parameters, and also taking the gradient with respect to the energy. So we do this semi-analytically at first and then evaluate each little chunk using Monte Carlo integration. The details you don't have to worry about too much for this little tutorial. Finally, we have an optimizer. So this is very similar to things you might have seen already in different machine learning contexts. To construct our optimizer, we need to specify the learning rate and give instances of all of the different classes we've constructed. And for every optimization step, all we do is sample from the wave function, calculate the average local energy and the error of the energy just to check whether we're at an eigenstate. And we also compute the gradient of the energy expectation value. And here I'm using optax in order to do the actual atom step. And to train, all I'm doing now is calling this optimization step many, many times. And I'm printing every 10th iteration. I'll also store the training so that we can visualize it later on. And finally, there's just one utility function here to animate the training history. So now let's move on to the actual toy problem at hand. We have one particle in a one-dimensional harmonic oscillator trap. This particular case is simple because you don't have to worry about any symmetries. If you had two particles, you'd have to worry about whether they're bosons or fermions, and then you have to make sure that your wave function has the correct symmetries. This necessarily will increase the runtime of this code, and I wanted something very simple for you to use. Also, one particle in one dimension is super easy to visualize. This system is also exactly solvable, so you can verify whether the wave function that you get at the end is the right one. So this is what our harmonic oscillator well looks like. I'm sure you're all familiar. And now let's construct all of our objects. The reason why we have a 1 at the beginning and 1 at the end is that we only have one coordinate for the one particle, and then our output is just a single real number. The numbers in between are up for you to change. So this means that we have 2 layers with 16 nodes each. You can feel free to change this to whatever you want. Personally, I don't like making these too large because there's usually other ways of increasing the flexibility of your neural network rather than just making it huge from the very beginning. If you can get away with a smaller network, that is what I have a preference towards. For the activation function, I've chosen GLU for confining parameter, just 0.01. You can change any of these numbers as you wish. The learning rate is 0.005, and I've also initialized my random seed here. Constructing all of my objects, it looks the same every time, except for the fact that for the Hamiltonian, I've inputted the definition of the potential that I want to use. And finally, I train, and I also just print off how long it takes to train in total. So let's run this cell. Um, for this very simple case, it won't take too long after it's done compiling the first iteration. You'll notice how much longer it takes for the first iteration compared to all of the other ones afterwards. But here the training just took about 40 seconds. And I've already created this animation, so let's just look at it. Because if you're following along in your notebook, the animation does take a little bit of time to generate. And let me also zoom out so that you can see a little bit better. So on the left-hand side, you see the wave function evolving as it trains. On the right-hand side, you see the corresponding energy. And the dashed black line here is the true ground state energy for the harmonic oscillator. So this is not too surprising. We end up with a Gaussian distribution at the end. But the point of this is that we have to, after we apply the necessary restrictions on our wave function, the training is actually very straightforward. But I said before that I wanted you to be able to experiment with any kind of potential you want. And so when you construct your own potential traps, I would like for you to try a variety of them, but my go-to was always a double well. And this can actually be pretty tricky unless your neural network is large enough. And also you're training slowly enough and you have a large enough sample size. So this is because with the double well, because we've exponentiated our output to make it positive definite, you run the risk of if you take too large of a step, then your wave function kind of can collapse on one side, and then you only have your wave function existing on the other. And this is just an artifact of having an exponential output. So you can do something smarter if you want. You can replace the exponential with soft plus and then train it pretty slow and delicately at first. But you can experiment. So I want you to get a feeling for how these neural networks train. I played a little bit with this version of a custom well. It's kind of like a weird bumpy one with a well within a well. I think this one where we have a square well is kind of interesting too. I've offset it so that you can see how the wave function moves side to side. This neural network I've made just slightly bigger, and I'm training for just a little longer, and I'm training a little bit more slowly than before. But for the most part, everything is roughly the same. So I'll let you run things on your own at this point. But you can see just from reading the values of the average energy and also the errors in the energy, they become very small. And in this case, you can see how the wave function moves from a more central location to the right side where the well is located. And one thing to think about is if my well only exists on like very far from the origin, but if I initialize my sampling such that there's very little overlap with this well, what would happen? Would your wave function train correctly? So these are all little details that you can get a feeling for using this notebook. And if you would like, I encourage you to see what would happen if you add another particle into the mix. See if you can, instead of having one input to your neural network, what happens if you have two, and how would your kinetic energy calculation need to change? Um, and with that, I hope you've enjoyed this very basic neural quantum state introduction. And if you have any questions, I'm happy to answer them now.
Thank you, Jane. If you have any questions, please add them into the chat and we'll be able to see them. Otherwise, thank you for attending and I hope you enjoyed it.
Thank you.
If you want to add your question to the chat, Shashi, then we can address it there. All right, do any of the remaining participants have any questions to share? You should be able to put them into the chat, and then Jane and I can see those. Jane, in the
Mhm.
Q&A, can you explain a physical significance of this 1D harmonic oscillators tutorial?
What do you mean by physical significance? Like if uh, for me, it was more of a example because it's exactly solvable so that you can convince yourself that it's actually working. So what do you mean by physical significance? Like if it can be physically realizable? Oh, oh, I see in the Q&A.
Yeah.
So do I type it
I mean, I
or
think you've
answer?
addressed it. Yeah.
Oh, okay, okay. I see. I see. Okay. Yeah, Shashi, for me, a harmonic oscillator, you have no interaction. You have exact solutions, which is kind of rare. And so developing a small little code for a situation like that is usually ideal. Then you can turn on an interaction and somewhat trust what's happening because you have nothing else to really compare to unless you have experimental calculations or something like that. But for me, the 1D harmonic oscillator is specifically chosen so that you can easily visualize what's happening. Even in 3 dimensions, having an animation that evolves would be very difficult to visualize, or even in 2 dimensions. 1 dimension is just perfectly interpretable.
All right. Any other questions from our remaining attendees? So I'm not seeing anything else. So thank you everyone for attending, and then thank you, Jane, for giving the tutorial. The materials will remain on the GitHub that Jane was showing if you want to go back through and review those.